Hi, my name is Brian Caff, and welcome to this week's Ask Brian, part of our weekly newsletter. I'm doing this week's this video on a Chromebook in my basement. I kind of don't have my recording equipment with me, so bear with me. I'm also just kind of figuring out how to do this on a Chromebook. So I'm going to answer a question this week because I got several requests where people asked, what is a p-value? And so I think this stems from two issues. One is this American Statistical Association white paper that came out in the journal American Statistician about kind of a policy statement about p-values from the American Statistical Association, something they don't do that often. And then secondly, a group of esteemed statisticians and scientists just put out a p-value or a paper about as much about null hypothesis significance testing as it was about p-values, but p-values were one of the primary points of discussion in the paper. And both of those things have generated a lot of news, especially on Twitter, if you run around in the kind of science and statistics circles. And so I think I'll do this in multiple parts to keep the videos kind of short. But the first question is, what is a p-value? So I'm going to cover this from two different angles. The first, and there's actually more than two different ways to think about a p-values, but there's two common ones. The first one is probably the way that it's almost always taught, which is the p-value is the probability of getting a test statistic or data, same sort of thing, as or more extreme in favor of the alternative assuming the null. Okay, so that's hard to think about. Why don't we do it in terms of an example? So imagine if I have a coin and you think that my coin is biased. And the kind of null hypothesis would be that the coin is fair. Why would you think it's biased? But you think it is. So we flip it 5 times and we get 5 heads. Okay, so what would be the relevant p-value in this case? And let's assume, to make this problem easier, that you think it's biased toward having more heads. Okay, so your obvious statistic, the data that you would be considering, would be the number of heads. So the p-value in this case, so our p would be the probability of 5 or more heads out of 5 flips, given the null hypothesis is assumed. So let me write it like that. Okay. So under the null hypothesis, the coin is assumed to be fair, so that we're going to assume that the probability of a head is 1/2, kind of not so much part of the null hypothesis, but part of the modeling assumed in the problem. We're going to assume that coins are independent and identically distributed. So 5 consecutive heads from a fair coin, they're probability 1/2 each. So that would be 1/2⁵, or 1/32. Okay, so that relatively small probability, 3% or so. So what does that mean? Well, that means if the null is true, it's unlikely we would get this many coin flips or this much data in favor of the alternative, or the test statistic this extreme in favor of the alternative. So that maybe casts doubt on the null hypothesis being true. Okay, and so that's the relevant interpretation of the p-value. If your p-value is small, then the probability, then you've either observed a rare event, your model is some way wrong, or the null hypothesis is false. Okay, another way to think about the p-value is the so-called attained significance level. So the attained significance level is, to talk about that, we need to talk about significance levels. So when we talk about a type 1 error rate, we're associating that with a test. So imagine, instead of flipping the coin 5 times and calculating the probability of getting 5 or more heads, instead of calculating the p-value, imagine if I said, well, I'm going to set up the procedure so that if I get so many heads, I will reject the null hypothesis and I'll pick that number of so many heads so that the probability of getting that many or more is 5% or less. Okay, so that's called a rejection region, and what we're saying is I'd like to control the probability that I reject my null hypothesis. If in fact it's true, I'd like to control that at a small value. 5% is maybe considered a small value. So I'd like to control that. That's so-called error rate control. I'm controlling my type 1 error rate in that case. Okay? So in that procedure, if someone were to tell you that they rejected the null hypothesis, all you know is that and that the type 1 error rate was 5%. All you know is that the statistic lied in the rejection region, but you don't know much more. And if you want to do the test at a different error rate than the person reported to you, then you wouldn't be able to change anything. You don't have the relevant information in most problems to actually do it. Okay, so what someone could instead give you, instead of just the result of the test, is they could say, what's the smallest error rate that I could have rejected for with the data that I saw and the hypothesis that I had. Okay, and that's the so-called attained significance level, the smallest type 1 error rate for which I could reject a null hypothesis. And it turns out that that's exactly equivalent to the p-value. It's just a different interpretation. But in this interpretation, all the p-value is it's a convenient way to present the results of a hypothesis test. If your p-value is 0.03, then that means you would have rejected for a 5% test, a 4% test, and a 3% test. Okay, but you wouldn't have rejected for a 2% test. And so it's a convenient way to give people the result of a test, especially because things like multiple comparisons. So someone could be reading your paper and they say, well, they probably should have controlled for multiple comparisons, but because I have their p-values, I can calibrate their type 1 error rate and control for multiple comparisons for them in my reading. If you only told them the result of the hypothesis test, they wouldn't be able to do that. So the attained significance level is just a different way to think about p-values. The top way I was talking about involves more interpretation, and the bottom one is simply a convenient way to report the results of a null hypothesis significance testing. So if people have problems with attained significance levels, what they're really saying is they have problems with hypothesis testing. And many people do for various reasons, some of them very good. And if people have problems with these kind of R.A. Fisher style p-values, then they're really saying, I don't like the way people are interpreting p-values. I don't like the way that people are thinking of p-values in terms of evidence and that sort of thing. So it's just a different problem that people have with p-values at that level. There's a third problem I would say that people tend to have with p-values is in misinterpretations of p-values. So I won't repeat that here because I don't want to plant the seeds of misinterpretations for people. But that's a third problem that people have, is that there's common misinterpretations, and those also get people riled up about p-values. So at any rate, if you want more about p-values, we have several Coursera classes. And like I said, in one of the next videos, I'll actually talk about some of the controversies and some of the statements that people are putting out. Probably the most recent one, I think, has more to do with hypothesis testing than it really does with the p-value itself. I think the paper is really saying we need to adopt a stricter standard for hypothesis testing. And it's interestingly signed on by many people who don't even agree with hypothesis testing. They're just saying we need a stricter standard. And they relate that to some other things, so-called Bayes factors. Okay, so that's enough on the p-value to just get you started. Look at some of these other classes if you want a more in-depth treatment. Make sure to sign up to the YouTube channel. Make sure to ask a question, and I'll see you next week.